Welcome to the Door of Fortune, a game show like no other. Our host, Pranav Chandra, welcomes Siddhant Sharma, our guest of the day. Now here's how the show works. Siddhant is faced with three closed doors. Behind one of these doors is a grand prize, a motorbike. Behind the other two are goats, which are not much of a prize. But Siddhant has no way of knowing which item lies behind which door. Whichever door he picks, he gets that prize. Siddhant is clearly hoping that he picks the bike, not the goat. Okay, here goes. He has picked one door, but he hasn't opened it yet. Now our game show host, who knows what is behind all the doors, will open a door which has a goat behind it. Now offers our contestant a choice. He tells him that he can choose to stick to his initial choice or he can swap. Now, does that make a difference? Should our contestant stick to his goats or swap? Welcome to a new episode of the Maths Factor, which is all about the wonderful world of luck, chance, or in mathematical terms, probability. So, what is probability? Well, here's a clue. What is the common factor in weather forecasts, sports, auto insurance rates, lotteries, casinos, and this problem? Quite right, probability. We're going to explore a gamut of ways in which probability populates our lives. But before we plunge into that journey, let's see how Siddhant is doing on the Door of Fortune. Siddhant is clearly in the haunts of a dilemma. Should he switch or stick to his first choice? Or do you think that it makes no difference? Once the host has revealed a door with a goat behind it, our contestant is left with two doors, one with a bike and one with a goat behind them. What should he do now? The answer is he should swap, as this in every situation will give him a greater chance of winning.
You have to make a choice. Think about it. Take your time.
Wondering why? Well, what Siddhant is facing is a classical mathematical dilemma known as the Monty Hall problem. But before we get to that, let's delve into the story of probability. Probability is a mathematical idea that populates a large part of our life. Let's see a few ways in which it is integrated in our day-to-day life. From figuring out whether it'll rain tomorrow, to calculating the health risks of smoking a packet of cigarettes, to deciding on the best investments for your money, to figuring out the odds, who will win a cricket match, to setting insurance rates, probabilities play a part in many aspects of our everyday life. Let's look at the most basic example. Here we have two teams of kids who are stepping out to play a game of cricket. The two captains step up to toss a coin to determine who bats first. One captain calls heads. Now what is his chance of winning? Well, that's what probability is. The likelihood or relative frequency of something happening. In this case, almost intuitively, we would say the chance of head falling is 50-50, which is absolutely right. And this captain, who had the odds in his favor, leads his team in to play the game. Now let's move to a game of Ludo. It's my turn. I need a 6 to get out of home and start my game. what is the probability that I'll get a 6? In a perfect die, all outcomes are likely. So the probability of getting a 6 is 1 by 6, which is the number of favorable outcomes by the total number of all possible outcomes. Now let's see how probability can help Bharti plan a picnic. Bharti is busy packing goodies for an al fresco picnic lunch with some friends, but is worried about rain. The weather report says that the chance of rain is 70%. Now what does that mean? Bharti is not sure whether it will or won't rain even with this information. It may help to understand where that 70% came from. Meteorologists predict weather based upon patterns. If our meteorologist has data for 100 days with similar weather conditions, and on 70 of these days it rained, a favorable outcome, the probability of rain on the next similar day is 70 by 100 or 70%. However, there is a chance it may not rain, which is 30%. The sum of the various probabilities must equal 1 or 100%, so if there is a 70% chance it will rain, there is a 30% chance it won't, which is what Bharti is banking on. In totality, it means that Bharti needs to warn her guests to bring rain gear for a picnic. Now, concepts of probability have been around for thousands of years. No one knows where or when the notion of chance first arose. In many cultures like ancient China, India and Egypt, elements of probability were applied to estimate the census of population or the overall strength of an enemy army. Astrogally also shows how the idea of chance was prevalent eons ago. Wondering what they are? Well, they are the heel bones of sheep and other vertebrates. Now, in archaeological digs throughout the ancient world, there has been a curious overabundance of astrogally. Why? Well, if we look a little closer at our astrogally, we notice that these odd-shaped bones have 6 sides that are not symmetrical. These were used as dice by priests as a way of divining the mood of their gods. Now, each combination was associated with a specific god and carried some advice. An outcome of 13344, for instance, was said to be the throw of the savior Zeus and was taken as a sign of encouragement. A 44466, on the other hand, was the throw of the child-eating Kronos, which sent everyone scurrying for cover. Ancient texts too talk about games of chance. For example, a game of dice played a key role in precipitating the Mahabharata war. In this famous scene, Yudhishthir, the Pandav prince, agreed to play a game of dice against the Kauravas, who have their wicked and cunning uncle Shakuni on their side. Through this game, Yudhishthir lost round after round, his kingdom, his brothers, and even his wife. Now, if we calculate the odds of Yudhishthir losing all the bids he made, it would have been pretty low. How the Kauravas won was because Shakuni used a pair of dice made from his own father's bones, which were magical, or using more prosaic terminology, loaded. What emerges is that the epic clearly has a notion of a fair game, hence some notion of unbiased dice and consequently probability. If we look at other cultures, in France, dice games are known to have been popular during the Middle Ages. Which brings us to an interesting story that led to the formal development of probability. The year was 1654. Our story starts off with a French nobleman by the name of Antoine Gambord Chevalier de Mere, who was fond of gambling. He used to play a game where he would bet on a roll of a die that at least 1 6 would appear during a total of 4 rolls. He used to win a fair amount of money with this. A bit bored with this game, he then attempted a variation. He bet that he would get a total of 12 or a double 6 on 24 rolls of 2 dice. But somehow he didn't make as much money in this variation. The Chevalier was puzzled by this apparent contradiction. Now he was a friend of Blaise Pascal, the famous French mathematician, physicist, inventor and writer. So he wrote him a letter asking why this new approach was not as profitable. Now this question sparked the birth of probability theory as we know it today. The problem proposed by Chevalier de Mere is said to be start of famous correspondence between Pascal and Pierre de Fermat. They continue to exchange their thoughts on mathematical principles and problems through a series of letters, and historians think that this exchange was the first documented evidence of the fundamental principles of the theory of probability. Some of the problems they discussed in this correspondence were: how many throws of 2 dice are required for a number of double 6 appear events that will be more than half of a total throws? How to share the wagered money between 2 gamblers if the game interrupted untimely? The method Pascal and Fermat developed is now called the classical approach to computing probabilities. This is what they worked out. Supposing a game has n equally likely outcomes, of which m outcomes correspond to winning, then the probability of winning is m by n. Using this, Pascal worked out the probability associated with Chevalier's problem. The probability of winning using the new approach was only 49.1% compared to 51.8% using the old approach. Here's an amusing extract from one of the letters of Pascal to Fermat. I have not time to send you the demonstration of a difficulty which greatly astonished Monsieur de Mere, for he has a very good mind, but he is not a geometer. This is, as you know, a great effect. In our journey through probability, I want to share a story by the famous horror writer Edgar Allan Poe. It is from his book, The Narrative of Arthur Gordon Pym. It centers on 4 survivors of a shipwreck who were in an open boat for many days before they decided to kill and eat the cabin boy, whose name was Richard Parker. Some years later, in 1884, the yawl Mignonette foundered with only 4 survivors, who were also in an open boat for many days. Eventually, the 3 senior members of the crew killed and ate the cabin boy. The name of the cabin boy was Richard Parker. Bizarre, right? This may be an extreme example, but our lives are peppered with simple coincidences.
सुहाना सफर और ये मौसम हंसी हमें डर है हम रह न
I'm sure you've
जाए
experienced
कहीं।
something along these lines. You're walking along, singing a song, and the same song suddenly comes on the radio. You're thinking of an old friend that you've lost touch with, and all of a sudden, out of the blue, you get a call from her. Now, we like the idea of believing that these events are special, that they have a deep meaning and significance in our lives. What we may not or do not want to acknowledge is that coincidences, even remarkable ones, are not at all that surprising. Let me tell you about one fascinating paradox to help us understand how probability works. For that, we need to head into a party. In the course of a conversation, you figure out that two people share the same birthday. Wow, how unusual, you think. Now, why do you think that is unusual? That's because the probability of two people sharing a birthday is 1 by 365, which is 0.27%. Very low probability, right? Now here's the paradox, which is aptly titled the birthday paradox. It says that in a room of 23 people, the chance that there are two people who share the same birthday is 50%. In a room of 75, that chance of overlapping birthdays increases to 99.9%. Wow, how is that possible? Now the chance of any pair sharing a birthday is 1 by 365. This implies that the chance of any pair not sharing a birthday is 1 minus 1 by 365, which is 364 by 365. That is 99.73%. So it's very likely that any pair will not share a birthday. Let's see how many comparisons we'll make across the room. For that, we need to look at our room of 23 people in a little more detail. When we compare our birthday with 22 other people in a room, we get 22 comparisons. But in this case, we need to take into account all the people in the room comparing with the others. So the next person will have 21 comparisons to make, since I've already compared my birthday with her. The third person has 20 comparisons, the fourth has 19, and so on. If you add up all possible comparisons, which is 22 plus 21 plus 20 plus 19 plus up to 1, the sum is 253 comparisons or combinations. Consequently, each group of 23 people involves 253 comparisons or 253 chances for matching birthdays. The chance of one pair not sharing a birthday is 364 by 365. The chance then of all 253 pairs not sharing a birthday is 364 by 365 to the power of 253. That is 49.95%. So the chance of a group of 23 people having one shared birthday is 1 minus 49.95% or 50.05%. So it's not really coincidence, it's just probability. Try it at the next party and you can figure if it works. And it makes for a good conversational gambit at least. Now, having journeyed through all these stories and ideas about probability, let's head back to where we started, to Siddhant and his dilemma. Let me refresh your memory. At the start of our episode, our contestant Siddhant was asked to choose one of the three doors. Behind one is a bike, behind the others are goats. He picks a door. The game show host, who knows what lies behind all doors, opens another, which has a goat behind it. Our contestant is then given the option of swapping. The question, should he or shouldn't he? The answer is he should, every time. Now let's figure out why by exploring both the options. Let's explore the different options when he chooses not to swap. One possibility, he chooses a bike in the first go. The host then reveals one goat. He doesn't swap, he wins a bike. Supposing he chooses one of the goats, let's call it X. Host will need to reveal the remaining goats, let's call it Y. If he doesn't swap, he stays with the goat. If he chooses the second goat, Y, our host will need to reveal X this time around. If he doesn't swap, he stays with the goat. Now let's see what happens when he does swap in all three options. He picks the bike first, the host reveals a goat, he swaps and ends up with a goat. He picks goat X first, the host reveals goat Y, he swaps and wins a bike. He picks goat Y first. The host reveals goat X. He swaps and wins a bike again. Let's look at all the choices in one go. If he picks a bike and swaps, he gets a goat. If he doesn't swap, he wins the bike. If he picks goat X and swaps, he wins the bike. If he doesn't swap, he lands up with a goat. If he picks goat Y and swaps, he wins the bike. If he doesn't swap, he lands up with a goat. So if he swaps, he wins 2 times out of 3. If he doesn't swap, he wins 1 time out of 3. So he should always swap to improve his chances of winning. You can use probability to run your life in every aspect. Did you know that the probability of being struck by lightning is less than that of winning an Academy Award? The probability of being canonized is less than the probability of winning an Olympic medal. The probability of being injured by fireworks is much lower than an injury from shaving. So whether we know it or not, we spend large portions of our lives making decisions based on probability. We don't have time for much more, but keep watching the Maths Factor for other fascinating ways in which maths propels our lives.